Okay, so for the last couple days, we've been talking about energy. Today, we're going to be talking about different forms of energy. So we've talked about mechanical energy, and we talked about the kinetic energy, and that was the energy of motion. Well, today we're going to talk about some other kinds of energy that we're going to be using. So there's three main types that we're going to be working with. The one is kinetic energy, and that's the energy of motion. So if something is not moving, it has no kinetic energy, and that's a simple fact. So if a car is driving down the road, it has kinetic energy. If it's stopped at a stoplight, it has no kinetic energy. So that's a real easy one for us to see. If it's moving, it has kinetic energy. If it's not moving, the kinetic energy is zero. The next one is gravitational potential energy. So we have two potential energy, and that's really the possibility that the object could have energy. It doesn't necessarily have energy at that point. It doesn't have kinetic energy at that point, but it has the ability to do kinetic energy or to do work. And we have two types. One is gravitational, the other is elastic and spring. Gravitational potential energy is basically energy that's stored based on the height of an object. So if we have an object that's located on the ground, so if this is our ground right here and we have a box that's located on the ground, it's not going to fall off the ground. It has no ability to move. But if I had an object that was up here on a ledge and the ground is down here, it has the ability to fall off that ledge and come down here. So if it's at a value of h, this is stored in the height that the object is at. Okay, so we're going to create gravitational potential energy based on where we want our 0 point to go. And we're going to talk about that in more detail in a couple slides. The next one is elastic or spring potential energy. So this is kind of like a slinky. If I pull a slinky as far apart as possible, it has the ability, if I let go of it, to go flying across the room. And so it has the potential to do energy. It's stored in the spring. Same thing as if I compress a spring like this, kind of like in a ballpoint pen. If I let it go, it's going to go flying. And so it has the ability, it's stored in the spring, its ability to have energy. So the three types that we're going to be working on are kinetic, gravitational potential, and elastic potential. Now there are other types of energy, but not that we're going to be dealing with in the mechanical side of the house. Okay, so first off, energy can be transferred from one form to another. And the way that we can show that is visually is by using bar graphs. So bar graphs are the graphs that come up like this. So we're going to use these to show that energy is being exchanged from one to another. So what we can do here is if I'm going to be looking at kinetic energy, and we're going to first start up here. So we have a guy standing on a diving board way up at this height, and this is going to be our height right here. So right now, if this is our 0 point, it has potential energy based on its ability to have height. And so we're going to have potential energy, but it's not moving. So the person isn't moving, so the kinetic energy is 0 before. And then the after, we're going to see that he's going down into the water and he has a velocity or motion going into the water. And so the after right here, the kinetic energy is maximum. So he starts off with no kinetic energy because he's standing still up here. So the V initial is 0. And then down here, the V final has a value and the kinetic energy increases. So you start with none and then the kinetic energy is going to be increasing. Well, now there's a relationship between kinetic energy and work, and we talked about this a couple slides ago, but the kinetic energy, the change in the kinetic energy equals the work. Okay, and we also know that work is the force times the distance. So over here, he has a lot of ability to do work because he's up here. It's the force times the distance. And at the bottom, when there is no distance, remember this is our 0 point right here. He has no distance. He's at the 0 displacement. Over here, his displacement is this much. So the work is maximum at the before spot right here, and then at the end it goes to 0. So you can see that the energy is being transferred from all this work is decreasing, and then at the end it's going to the kinetic energy. At the beginning he has tons of work or ability to do work, which is potential energy, and at the end everything is in the kinetic energy. So we're transferring the energy from one to the other. Okay, so So let's talk a little bit more detail about kinetic energy. So we have the equation kinetic energy equals 1/2 mv squared. Sometimes you'll see just the K, but most of the time you'll have kinetic energy, 1/2 the mass times the velocity squared. So we want to look at these equations. First off, the units that we have for kinetic energy is joules, and it's a scalar quantity. Okay, which means it has no direction, it only has the magnitude. Because if the velocity is negative, if you take a negative velocity and you square it, you're still going to have a positive velocity. So what we have is this equation right here, or this question here. If we have two objects that are moving, they're moving, so we have kinetic energy with the same velocity. One has a greater mass, which one's going to have the greater kinetic energy? Well, right here, the kinetic energy and the mass are equally proportional or directly proportional. So as the mass increases, the kinetic energy increases by the same amount. So the one with the greater mass is going to be the one with the greater kinetic energy. The least amount of mass, the lesser amount of kinetic energy. Now let's take another scenario here. We have two objects with the same mass. One moves with twice the velocity of the other one. What is going to happen to the kinetic energy? Well, if you look here, the relationship between kinetic energy and velocity is no longer linear. It's not a proportional equation. What happens to the kinetic energy is exponentially in relationship to the velocity. So as velocity doubles, the kinetic energy is going to quadruple. So pretty much if the velocity doubles, you're going to square the whole velocity and you end up with 4v squared. So this is, the kinetic energy will increase by 4 times, or it'll quadruple. There's one other form of energy that's part of kinetic energy, and this is rotational kinetic energy. So if you took like a top and you were to spin it around, it doesn't have motion in this way, and so we think, well, it has no energy. But there is energy when you spin this thing. So we have what's called rotational kinetic energy, and it's really the same equation as this. It's 1/2 I, which is your moment of inertia, times omega squared, which is your angular velocity. So you can see that the 1/2 is the same. The mass is equivalent to a rotational moment of inertia, and V and omega have that same relationship as well. Okay, now we're going to get into more detail about potential energy. So we're only going to talk right now about gravitational potential energy, and we use PE, and sometimes, so that's potential energy, sometimes you'll see U with a G here. So this would be a gravitational potential energy here. Well, the equation for that is just mgh. It's the mass of the object times the gravity, which is really the force, times the height that it is from the ground. So if I have an object that's up at this high, it's going to be this distance right here. This also is a scalar quantity, meaning there's no direction to it, but we are going to talk about that you could have negative, but that just means it's against the grain, kind of like we could have negative work. The units for energy is joules, so the units for gravitational potential energy is joules also. But if you look here, the equation for work is force times distance. Like the stair exercise that we did, this force was our mass times our gravity, and the h was the height that we walked up the stairs. So if you can see that these two equations are the exact same. So we can say that the work is equal to the change in potential energy. Very similar to the equation that we said work is equal to the change in kinetic energy as well. Okay, so we have two nice equations that we can work with over here. Okay, so this is kind of a confusing slide, but we'll go through it step by step. We're going to be talking about what happens when you throw a ball up in the air and it goes around here. So this could be thrown straight up and straight down or in a parabolic motion. So we're going to start, this is going to be at the very beginning. This is going to be the middle when the ball is at the very, very top, and this is going to be the end. So we're going to look at this first, so we ignore that. So at the very, very beginning, this ball is thrown up with an initial velocity. The velocity here goes to 0. Remember, we talked about the velocity at the very top is 0, and then down here the velocity is v final, which is going to equal to v initial. So before, if this is our 0 mark right here, there is no potential energy because it's at 0. The height is 0. So the potential energy is 0 right here. Now the kinetic energy is right here, and that's equal to 1/2 mass times velocity initial squared. Once it reaches the very top of its projectile, the V is 0, so the kinetic energy is 0. Now the potential energy, which is right here, is m, g, and h is this distance right here. And we're at its maximum height, so the potential energy is maximum at this point. And then back down here, our potential energy is back at 0, so our potential energy is 0, and our kinetic energy is 1/2 m. And it's negative v squared, but you can see that that comes out to be a positive v, so these two, the energy is equal. So what you're going to be seeing is this relationship that the kinetic energy is here, and as kinetic energy decreases, potential energy is increasing, and then eventually you're going to have maximum potential energy and minimal kinetic energy, and then it's going to go back down again. So there's this equal relationship here. As one goes up, the other goes down. Okay? And this graph now is done the same way, but the only thing I've changed is I've changed my 0 point. So the nice thing about energy is that we can choose where we want our starting point to be. So let's assume up here now is 0. And this now is going down, so it's a negative h. So if you look here, when the ball starts right here, the kinetic energy that it has is 1/2 mv squared, and we have the v initial. So we have kinetic energy here, which is 1/2 mv initial squared. Once it reaches up here now, let's talk about the potential energy here. If this is 0, we have potential energy, which is mg negative h. Okay, the negative does not tell us it's going in the opposite direction like a vector would, but the negative is telling us that we're below 0. Okay, so we have negative mgh. Then we're now at the top over here. Kinetic energy goes to 0 because velocity is 0 at the top. Well, potential energy is mgh. Well, it's at our 0 point, so that's at 0 as well. And then once we come down here again, we're the opposite of the initial situation. So in this case now, we have maximum kinetic energy at the beginning and very, very minimal potential energy, and now we're going to be going like this. Okay? So it really is the same thing, it's just based on a different starting point. Okay, so let's try an example. Okay? How much work does a bricklayer do to carry 30.2 kilograms of bricks from the ground up to the 3rd floor of a building under construction? So the first thing we want to know is how much work. So we're looking for the work. The mass is 30.2 kilograms up a 3rd floor, which is 11.1 meters. That's our height. So the first thing we want to do is we want to find our work. Well, we're going to go back to that equation that work is force times distance times cosine theta. So this is very similar to the lab we did. Here's the guy starting over here, and the work that he does is going to be his force, which is mg. And the distance now is going to be the vertical distance that he's going to be going up. So we're looking for this distance right here. Okay, which is 11.1. Oops. So this will be just the distance. So we know the mass is 30.2 kilograms. We have to multiply it by gravity, 9.8 meters per second squared. And then we're going to multiply it by the distance, 1.1 meters. I'm sorry, 11.1 meters. So the work that it takes for him to carry this load of bricks up is 328.5. Sorry about that. I think I've got an extra 8 here. 0.16 joules. So that would be our answer, 3,285.16 joules. Now the second part of the equation, well, what is the potential energy of the bricks when the bricklayer reaches the 3rd floor? So we want to know what is his potential energy here. Well, his potential energy is mgh. I'm going to write down here, it's a little easier. Potential energy is his mass, which is 30.2 kilograms. The g is 9.8. meters per second squared, and the height is 11.1 meters. I multiply that out, I end up with 3285.16 joules. And you'll see that they're the same. And that goes into our equation that work equals change in potential energy. Okay, so the potential energy here is 0 because we're going to say that this is our starting point of 0, and the potential energy up here is your P final. So this minus 0 is just 3285, which gives us the work equals the change in potential energy. So if I were to take the same thing and draw a bar graph, I could show that right here, let's see, we'll go here. When he's at the bottom, he has kinetic energy. Way up here, he has no potential energy because he's sitting at the bottom. And then at the top of the stairs, he has no kinetic energy and maximum potential energy. The potential energy here is the 3,285.16 joules. So we can able to solve these equations. So what we're going to be talking about next is, well, how are we going to find out what that kinetic energy is? So we know that the potential energy is 3,285.16 joules. What do you think that kinetic energy is going to be? And we're going to be talking about conservation of energy next. Okay, so we'll see you tomorrow, and don't forget homework assignment on the for video 10, and that will be due tomorrow. We'll see you tomorrow in class.